Hello class, this is Mrs. Ayodeji with today's video on section 10.5 Fourier series. As you're watching the video, please write down important vocabulary, formulas, equations, and notes. Feel free to pause, rewind, or replay the video as often as you need so you can get a clear understanding of what is occurring. And at the conclusion of watching the video, write a brief summary of what occurred in the video and submit that summary via the online whisk. All right, let's begin. So as you know, we've been working with Taylor polynomials to approximate functions. And Taylor polynomials are very good if you want very good local approximations of a functions using easily computable functions like polynomials. But what if your function is not differentiable continuously or may not be differentiable on the interval? Then Taylor polynomials are not effective for those type of functions. Because in order to use Taylor polynomials, the functions need to be continuously differentiable, i.e. have as many derivatives as we need. And not always are all functions in real life situations going to be continuously differentiable indefinitely. And so we're going to talk about a method to approximate functions that aren't necessarily continuously differentiable or differentiable on an interval, or functions that we really want to know not just for a small interval, we want to be able to approximate it just overall totally. And in other words, good global approximations. And so in order to do that, we're going to use a type of functions called Fourier functions, which was developed by the mathematician, I think it was Jacques Fourier. Okay, and we're not going to derive them because we'd be here forever, but we will do GEAs to discuss how they came about. All right, so let's take a look. The reason why Fourier became about the functions is because a lot of times in real world situations, the functions that we deal with are periodic, which means they repeat over a certain interval. And so if you can get a good approximation of a period, then you're done for the infinite rest of the interval of the function because it's periodic. And so here an example is the model for electricity flow for a light switch. You know, as I turn on and off the light switch, what's the intensity of the electricity? And when of course the electricity is on, it's the highest intensity. When it's off, it's the lowest intensity of 0. So if I'm regularly turning that light switch on and off, then the model for the electricity flow looks to be very much like this type of function. We call it a square function. Okay, and it seems to be that this function is also periodic because I'm constantly turning the light switch on and off for a set interval. And using a Taylor polynomial to approximate this function would not be efficient because, number one, this function is not differentiable at certain values on the period. As you can see here, where values is 1, 2, we have limits going from both directions, so it's not differentiable. So we can't really use a Taylor polynomial because we don't have a Taylor function that describes this accurately. So if I do want to take a look at the function, and here are two examples of two different types of functions. This is a square function, wave function. This is a triangular wave function. And as you can see, it's very piecewise, different pieces, or we also call it a step function. How can I approximate this function using some other functions that we know that we can easily compute? Okay, so let's do an example for this. So to make life simpler, let's say instead of that the light switch is being flipped on every 1 second, it's being flipped on and stays on for pi seconds and stays off for pi seconds and then stays on for pi seconds, vice versa. And so we have this function can be represented by this: 0 meaning no intensity, 1 being high intensity. Okay, and this is just one interval or one period of the function, and we can keep repeating this for multiples of pi and vice versa. Okay, so can I represent that? Well, we're going to use what's called a Fourier polynomial, and we call it polynomial, but it's really not a polynomial at all because it's not the result of a sum of polynomial terms. In fact, it's a result of a sum of trigonometric terms. Because remember, we're dealing here with a periodic function, and the most popular periodic functions are trigonometric functions. And so the most simplest trigonometric functions are sine and cosine function. So this Fourier polynomial of degree n is a combination of sine and cosine functions of different varying degree. And this is what it looks like in essence. And you have this starting value, and then you have a sine term and you have a cosine term. So here's my cosine term and here's my sine term. Okay? And really, in order to be able to come up with the Fourier polynomial, it's really all about the coefficients. And this is where it's the tricky part. The coefficients, a sub k and b sub k, can be found by something even trickier. Okay, so this is not an easy process computationally, but it is a process that can be done. So as you can see, the Fourier coefficients, there's two types, the A coefficients and A naught, A1, A2, A3, all the way up to AN. That's related to cosine. And then we have the B coefficients, which is related to sine. So that's the easiest way to refer to them. And the K term will not only indicate the term of the coefficient, but it also represents the multiplier of x in each of the functions. So this is for the second term, third term, vice versa, nth term. Okay? So now, of course, the common question is, how do I determine these Fourier coefficients? Okay? Well, get ready for your pen and pencil because it's a doozy, but it's actually not difficult. It's just a lot. So let's just start with a periodic function that has a period of 2 pi. It makes life a little bit easier for right now. So to figure out a naught, we basically take the interval from negative pi to pi of f of x, and we divide it by 2 pi, which is the period. To figure out just a sub k in general, it's 1 over pi, the interval from negative pi to pi of f of x times cosine k of x. Remember, a is represented or related to cosine, okay, as long as k is greater than 0. And then anyone guess what b sub k is going to be equal to? It's going to be equal to 1 over pi, the same exact thing, except instead of cosine, we're dealing sine. And depending on what k is, k of x, okay? Two things to note, even though a naught is part of the coefficients, there is no b naught. Second thing to note is that the number of the term also represents the number of the multiplier of the trigonometric function in the period, okay? So FYI about that. So this is what you need to know. Now, what does these numbers represent? Well, a naught represents, you might recognize this as the average value of a function over an interval. In this case, the interval is 2 pi, so this is why we divide it by 2 pi. But this is represents, since this is symmetric from negative pi to pi, not the function, but that's the average value, okay? All right, so now let's use this. Hopefully you've written it down and we're ready to use it. So in order to use this, we got to remember how to determine the coefficients if we're going to come up with a Fourier polynomial, and that's in quotation marks, okay? Make sure you know that. So in example 1, they want us to construct Fourier polynomials for the square wave function with period 2 pi, okay? So this is the function. The only thing different from the previous graph is instead of intervals, you turning on the light every 1 second, now we're turning on the lights every pi seconds and vice versa, okay, to make life easier. So to determine a sub naught, we use the exact same formula we talked about earlier, 1 over 2 pi, negative pi to pi of f of x. Now, because this breaks up the interval defined, we're going to have to break up this integral from negative pi to negative pi to 0, and then from 0 to pi. Okay, but the good thing is we have a bunch of zeros, so we love the zeros. We don't have to evaluate that. That's just 0. And then this when we evaluate that, that's just 1 over 2 pi pi. So you get a total of 1 over 2. That's my a naught. You do the exact same process for a sub 1. The only difference is instead of 1 over 2 pi, it's 1 over pi. And instead of just the function, it's the function times cosine. Oops, sorry. It's the function times cosine. Evaluate that integral, life is good, it's a 0. We go through the same process for b sub n, b sub 1. The only difference is b sub 1 involves sine, not cosine, and we get this expression. Okay, so now we are ready to come up with our Fourier polynomial of degree 1, because remember it's a naught plus a1 times cosine, all the sums of the cosines plus b1 times the sine of the cosine. Sorry, sine of the cosine. Well, is this right here? So if that's the case, this is what our expression looks like using our, our a1. So our final answer looks something like this. Bam, there it is, nice and easy from our a naught and our a1, which was 0, and our b1, which is 2 over pi sine x. And when we graph it, it looks like this. Okay, so this is our our Fourier polynomial of degree 1. Pretty, isn't it? I think so. All right. If I want to do degree 2 Fourier polynomial, I evaluate a 2 and b sub 2. Again, the only difference is instead of cosine of x is cosine of 2x, instead of sine of x is sine of 2x, and we end up with it both being 0. So that means that the first and second order Fourier polynomial are the same. To continue this, we move on to the third degree, and that means we have to figure out a sub 3 and b sub 3. And we end up with these calculations. And so now we can write our third order or Fourier polynomial, or our third degree Fourier polynomial, f sub 3, to look something like this. And the graph of this is to the right. And as you can see, it looks a little bit better to approximate the sine, the square wave function as before. Okay? So if we want to go on, if we have no life, we can do f sub 5 and f sub 7. And then if we take a look at their relative graphs, we can see how as you increase in the order of the Fourier polynomial, the graph gets bigger, better approximation as a whole over the period. Again, not at any particular one value. Okay? All right, so in conclusion, well, this is just the series, the simplest case, the Fourier series for f on negative pi and pi. It's the same process. I don't know why I put that there. Let me move on. We can keep doing this process, or we can come up with a sequence or a series based off our coefficients, either which is just fine. I'm not going to talk too much about harmonics, but because that's a more applied sense, but they call this the kth harmonic of f, which is the term involving the kth cosine k of x plus b sub k sine k of x. Okay, and so the first harmonic is a simple harmonic, a1 cosine x plus b1 sine of x, and you'll see that in applied cases like sound waves and things of that sort. So one question you may be asking is, what happens if our function does not have a period of 2 pi? The formula I gave you was for functions that have a period of 2 pi. Well, it's the same formula with some very slight changes, okay, and the slight changes can be looked at simply in this term right here, okay? And the 2 pi over b, if you guys recall, that's related to the period of a function. So for the period of 2 pi, b was easy to see, it was 1. But now if b is not 1, then you're going to have a period that's not 2 pi. So it's the same process. You just have another variable b that we've used back in pre-calculus. And here's the rest of the function coefficients. And that's it. So we'll be doing a lot. Don't worry about the VA. We're not going to have an actual VA on this. We will spend most of our time on a GEA since this is an applied problem. All right. Hope you enjoyed it. Bye-bye.